Physics is experience, and one of the best places to experience physics is Hersheypark. We hope that this video will help prepare you to get the most out of your Hersheypark Physics Day experience. One of the first things you'll notice at the park is that things are moving. But what is motion? Motion is a continuous change of position relative to a reference point.
Right now.
Take a look at this next clip several times and see how many different examples of motion you can observe and describe.
Right now. It's going to be like just a slope area, right?
Right
now. It's going to be like just a slope area, right?
One type of motion you can experience at Hersheypark is the relatively constant, relaxing motion of rides like the monorail or Skyview. But most people go to the park to experience changes in motion. What causes objects to undergo these thrilling changes of motion? The answer is pushes and pulls, which are commonly called forces. We're using the arrow to represent a pulling force, because in reality, you can't see forces. You can only observe the effects of forces on objects. In summary, forces are pushes and pulls. Motion and forces aren't enough to explain everything that happens at the park. The basic question is, where do objects get their ability to move and to change their motion? Energy. Energy is the ability to cause change. Moving objects have energy. In other words, they can cause change. A moving tidal force boat can definitely cause the water to change what it's doing. Scientists call energy of motion kinetic energy. Objects can be positioned in such a way that they store energy. This stored energy has the potential to become kinetic energy. Therefore, scientists call stored energy potential energy. The higher an object is off the ground, the more potential energy it has. Machines help to supply energy. Here's the machine that transfers energy to the tidal force boat. Complex machines consist of combinations of simple machines, like levers, gears, pulleys, and ramps. Energy transfers and conversions from one form to another are common. At Hersheypark, you will witness a wide variety of energy conversions. Notice these dolphins using the chemical energy stored in their food to produce entertaining displays of kinetic and potential energy. Roller coasters rely heavily on energy conversions. They constantly transfer energy from potential to kinetic to potential again. So far, we've laid the foundation for your Physics Day experience. A basic understanding of the three concepts of motion, forces, and energy draw physics students to Hersheypark. But the curious mind craves more detail. The detail is to be found in numbers. When you can measure what you are speaking about and express it in numbers, you know something about it. Where do physics students get the numbers they need to develop a better understanding of the basic concepts? They use measuring devices. Some of the tools that will be helpful at the park include vertical accelerometers, horizontal accelerometers, and stopwatches. In addition to the measuring devices, students will need a pencil or pen, an organized place to record their data, and a calculator to help process the numbers. What do students do with the measurements once they have them? They use physics formulas and their knowledge of mathematics to calculate other quantities about the rides which are not easy to measure directly. One such quantity that students determine on Physics Day is the speed at which rides travel. The average speed of a ride is defined as the distance the ride travels divided by the time it takes to travel that distance. Velocity is another word you may have heard used when discussing motion. Many people believe that speed and velocity are synonymous. There is, however, a subtle difference. Speed deals with distance and time. Velocity deals with distance, time, and direction. Common units of both speed and velocity include miles per hour and feet per second in the English system, and kilometers per hour and meters per second in the metric system. Let's use the Wildcat as an example for determining average speed. The Wildcat contains approximately 3,000 feet of track, and the ride takes about 2.5 minutes to complete. Using the equation for average speed equals distance divided by time, and plugging in the numbers, we get an average speed of about 20 feet per second. In the metric system, the track length is approximately 950 meters. Dividing the distance in meters by the time of the ride here yields an average speed of 6.3 meters per second. In addition to determining the average speed of rides, students are frequently asked to determine the speed at particular points along the ride. These speeds at a point are called instantaneous speeds. As an example of determining a speed at a point, the speed of the super-duper looper just before entering the loop can be determined if we know the length of the looper train. By picking an easily identifiable point on the track, like the blue loop support shown here, and timing how long it takes the train to pass that point, the speed can be calculated by dividing the length of the train by the determined time. The length of the train is 13 meters, and the time it took to pass the reference point was approximately 0.5 seconds. The speed that the train had when it passed this point can be determined by using the speed equation. Dividing the distance, 13 meters, by the time, 0.5 seconds, gives a speed of 26 meters per second. Now you try one. Using a stopwatch, time how long it takes the looper train to pass a reference point at the top of the loop. Remember to start your stopwatch when the front of the train reaches the reference point, and stop your stopwatch when the back of the train passes the reference point. Once you have determined the time, use it and the length of the train, 13 meters, to determine the speed of the looper train at the top of the loop. We measured the time to be about 1 second, which yields a speed of 13 meters per second. Motion from point A to point B is called translational motion. Circular motion occurs when point A and point B are at the same place, and the path traveled to get from A to B is a circle. The distance traveled in completing a circle is called the circumference. This distance can be calculated using the equation circumference equals pi times the diameter. Since the diameter of a circle is twice the radius, the distance can also be calculated by multiplying 2 times pi times the radius. The time it takes an object to complete one circle is called the period of the motion. The average speed of a rotating ride can therefore be determined by using the same equation as before for speed equals distance over time, except that the distance traveled is the circumference, and the time used would be the period. It's your turn again. Using a stationary reference point, like the bottom of the ride, time how long it takes a given car of the Cyclops to complete one circle. Given that the radius of the Cyclops is about 24 feet, determine the average speed at which riders are traveling. Objects in general, and park rides in particular, do not travel at the same speed all the time. Objects speed up and slow down. When an object changes its motion, we say it accelerates. Average acceleration can be defined as the change in speed divided by the time it took for the change to occur. The change in speed is determined by subtracting the initial speed from the final speed. To determine the acceleration of a Hersheypark ride during some segment of its motion, you must know the starting speed, ending speed, and the time for that segment in which you were interested. For example, we previously determined the speed of the super-duper looper train at the bottom and the top of the loop. These values were 26 meters per second at the bottom and 13 meters per second at the top. The time for the train to get from the top of the loop to the bottom of the loop is about 1.5 seconds. The acceleration can be found by subtracting 26 meters per second from 13 meters per second, and then dividing the result by 1.5 seconds, which gives an answer of negative 8.7 meters per second per second. In other words, the train loses an average of 8.7 meters per second of speed every second of time that it's going up the loop. Negative accelerations of this type are often called deceleration. Accelerations also occur when objects change direction. If an object is going in a circle at constant speed, it is still said to be accelerating because its direction is constantly changing. The direction of the acceleration is toward the center of the circle and is therefore called a centripetal acceleration. Rides like the Pirate undergo patterned speed and direction changes. This kind of accelerated motion is called periodic motion. There are equations for determining centripetal and periodic accelerations. However, they involve more depth than this video can cover in the time available. Calculating accelerations can often be a rather involved and time-consuming process. A different approach to determining accelerations is to use an accelerometer. Accelerometers use the acceleration of gravity as a reference value. Objects in freefall, influenced only by gravity, will gain 32 feet per second of speed every second of time that they fall. In the metric system, this acceleration is 9.8 meters per second per second. The symbol g is used to represent the acceleration of gravity. Accelerations are then measured on accelerometers as the number of g's experienced. Typical accelerations measured on rides at Hersheypark range from less than 1 g up to 4 g's. The tendency of objects is to maintain consistent motion. If an object is at rest, it tends to stay at rest. If an object is in motion, it tends to continue in the same straight line motion. The tendency of objects to keep doing what they are already doing is called inertia. Some objects have more inertia than others. Objects with more inertia have a greater tendency to maintain their state of motion than other objects. Mass is a measure of an object's amount of inertia. Objects with more mass resist changing their state of motion more than objects with less mass. An empty coal cracker boat will slow down faster at the bottom of the flume than will a boat full of people, since the inertia of the filled boat is greater. In a collision between a low-mass bumper car and a high-mass bumper car, the lower-mass bumper car will experience a greater change in its motion. It is net pushes and pulls acting on an object which cause the object to change its motion. In other words, accelerations, changes in speed and/or direction, are caused by net forces. Net forces can be calculated using the equation net force equals mass times acceleration. If the same amount of force acts on two different masses, the smaller massed object will experience a greater acceleration. Its state of motion will change more than the larger massed object. There are many forces acting on Hersheypark rides, from tension forces in cables that hold up riders to contact forces between wheels and tracks. Two very important forces experienced at Hersheypark and in daily life are gravity and friction. Gravity is the Earth's pull on an object. It is the driving force behind many rides at the park. Gravity is a natural force to utilize for park rides, since it is free to be used for fun and enjoyment by all people at all times. The force of friction helps to keep gravity in check on rides. Without friction, rides like roller coasters would attain dangerously high speeds and be very difficult to stop. As you might have guessed, there are equations for determining numerical values for the force of gravity and the force of friction. Knowledge of these equations can give you a better understanding of the concepts involved in dealing with forces. The man who first pulled together the concepts of forces and motion was Isaac Newton, a 17th century scientist. Newton summarized his ideas in his 3 laws of motion. The first law states that objects in motion tend to stay in motion, and objects at rest tend to stay at rest unless acted on by a net force. The second law states that net forces cause objects to accelerate, And the third law says that for every action, there is an equal and opposite reaction. Unfortunately for Isaac Newton, he did not have the opportunity to experience the application of his ideas at Hersheypark. But you can. See you at Hersheypark Physics Day.
Fun comes from different places. Hersheypark turns a